Hi, good morning, good afternoon, good evening, class. This is Mr. Arosena, and today we're going to be talking about how to balance redox reactions using oxidation numbers. I've already discussed with you guys how to balance redox reactions using half reactions, and as we saw when we were doing that, some of the reactions could get a little tedious. With oxidation numbers, this is a technique that is somewhat faster in some cases. Other cases, it's actually harder because it's sometimes difficult to spot what's actually being oxidized and reduced. The oxidation number method is very useful, especially in cases where you can identify what's being reduced and what's being oxidized really easily. If you can't identify what's being oxidized or reduced easily, then the half reaction method is usually better. Albeit it is, again, like I said, tedious, but it's easier or sorry, I should say easier. It's more robust, I guess. Will always work. It'll always work, I guess. This method, useful if you know what's being oxidized or reduced. Anyways, to use this method, we have to go through a few steps, much like with the half reaction method. And the steps are somewhat different. At least the first couple of steps are different. So the first step is to determine the change in oxidation numbers. Now this actually requires you to assign oxidation numbers first, so you can actually figure out what's actually changing. So you need to assign oxidation numbers first. And you have to assign this to all elements. Okay. So as an example, well, I'll go through an example later. Okay. All right. Step 2, once you've determined the change in oxidation numbers, we need to balance that change. Okay, what I mean by this is that in every oxidation reduction reaction or pair, you're going to have something that gives away electrons, so its oxidation number will get more positive, and then you'll have something else accepting those electrons, so its oxidation number will get more negative. However, everything has to be balanced, so any positive change, so any positive change in oxidation numbers must be met with an equal negative change. Alright, so if something gains a charge of +2, there must be a total net change of -2 from something else. Now, in a lot of cases, you will get something like something's gaining a charge of +3 and something is losing, or yeah, something is, yeah, oxidation number is changing by +3 in one case, and in another case, it might be changing by only +1 or +2 or +4, I guess. It would be negative change, I guess. Yeah, so something might gain a +3 change, something else might gain a -2 change. Those don't really balance out, so we have to figure out a way to balance the change in oxidation numbers. This will usually involve a multiplication of both. Yeah, multiplication, so that the positive change ends up being equal to the negative change. Okay. All right. Now the step 3, is to then basically balance major atoms. Okay, just like before, major atoms are the non-oxygen, non-hydrogens. Fourth step, balance oxygens using water. Okay, and step 5, balance H pluses, or H's using H plus. Okay, so it's much the same as before. So the first 2 steps are different, but then all the other steps after that are exactly the same. And then finally, if step 5b, if basic, use the water equilibrium, or depending on how your equation works out. You're going to use one of those two equations to convert it from an acidic situation to a basic situation. All right, so those are kind of the five-ish steps that we would perform to balance a full redox reaction using oxidation numbers. All right, let's go through an example. In this example, we are going to balance the following. So let's balance this reaction. Fe2O3 plus CO going to Fe plus CO2. Alright, so let's assign oxidation numbers first, because we need to assign oxidation numbers so that we can determine what the change is. Okay, we'll start with here, with the Fe2O3. The oxygen has an oxidation number of -2, because that's what oxygen does. Iron, when in this particular compound, will then have an oxidation number of, let's see, the 3 oxygens times -2 is -6. So the irons will have a total oxidation number of +3 each. Each of them will have an oxidation number of +3. Okay. Over here, in the carbon monoxide, oxygen has an oxidation number of -2. Carbon has an oxidation number of, in this case, +2. Okay. Over here, on the product side, the iron, the lonesome iron, has an oxidation number of 0 because it's by itself and has no charge. And the oxygen here, still the same thing, -2, but this time the carbon changes to a +4 because we have 2 oxygens with -2. The carbon must have a +4 then because carbon dioxide has 0 charge. All right, so now we know the oxidation numbers. So the ones that are changing are as follows. So the iron is going from a +3 to a 0. So it has a total oxidation number change of -3. Okay, and that kind of makes sense because it's here it has in the iron 3 oxide it has a effective charge of +3, and then as in solid iron it now has a charge of 0. The carbon on the other side has a total oxidation number change of +2 because it's going from +2 to +4. Okay, so that's step 1. We determined the change. Now we've got to balance the change because again, whatever is being given up has to be absorbed somewhere. So if the carbon is giving up +2, well, it has to be absorbed by the iron. However, the iron needs to gain 3 electrons to perform this reduction reaction. Okay, so we can't just do this carbon reaction once. This carbon has to, 2 carbons have to give up electrons. But if 2 carbons give up electrons, the carbons will end up giving up 4 electrons as opposed to just giving up 2 electrons here. Okay, so it can't just be 2. So if I give up 3, so if this reaction occurs 3 times, that'll give me a total oxidation number change of +6, which I can easily match down here if I do this reaction twice. And so if both of these irons absorb the electrons, then this can occur. So in order for the +2 change to occur 3 times, I need 3 of the, let's write that in blue. I need 3 carbon monoxides, because the carbons are going to be the ones giving up the irons. Or not the irons, the electrons. So I need 3 carbon monoxides giving up 2 electrons each to become 3 carbon dioxides. Then, those 6 electrons are going to be absorbed by 2 irons. That's what this 2 here is signifying, is that 2 irons are absorbing 3 electrons each. Okay, now we've already got 2 irons here, so I don't need to do anything to this side. But I do need to put down 2 irons here, because on the product side I only had 1 iron, but we need this to occur twice, so I'll put down 2 here. Alright, now we check to see if our oxygen or our major atoms are balanced. The ions, by putting the 2 there, the ions have balanced themselves out. Okay, so ions are balanced. Step 4 was to balance the oxygens. So let's count the oxygens. I have say 3 oxygens here plus 3 oxygens here, so a total of 6 oxygens here. On this side, on the right side, I now have 6 oxygens here. So oxygens are balanced. There's no hydrogens to balance, so this is good. So my balanced equation will look like this. Fe2O3, let's move this up a bit. Oops, not too far. Fe2O3 plus 3CO going to 2Fe plus 3CO2. There you go, fully balanced equation. Okay, let's go through another example. Okay, in this example, we're going to balance the following example. So balance Cr2O7 2 minus plus SO3 2 minus going to Cr3 plus SO4 2 minus. Okay, so let's start off by figuring out the oxidation number change and everything. So we'll start with the oxygen. That's relatively easy. Oxygen is -2. Chromium, well, we need a total charge of 2 negative. The oxygens are providing a charge of -14. So the chromiums have to provide a charge of +6. Or not +6, +12. And because we have 2 chromiums, each of them gives a charge of +6. Okay. We'll make it easy, we'll just skip over this side. The chromium here has a charge of +3. Alright, now in this compound, the oxidation number of this oxygen is still -2, while the sulfur has an oxidation number of, let's see, if we go to -2, so the 3 oxygens are providing a total charge of -6, so the 1 sulfur needs to have a charge of +4. Okay, repeat the process here. This is -2 for the oxygens, so the sulfur ends up being +6. Alright, now the change. So this sulfur has a total oxidation number change of +2. Okay. And then this chromium has a total oxidation number change of not +3. What am I talking about? It's going from +6 to +3, so it's going to be a change of -3. All right. Now, much like before in the previous example, we've got to multiply these so that the changes are the same. In this case, same thing as before, so this will be have to multiply by 3. This will have to be multiplied by 2. Okay, so again, the multiplication basically just says that each of those reactions has to occur that many times. So with the sulfur one, there has to be 3 of these oxidation changes. So in order for that to occur, I'll need 3 sulfite ions turning into 3 sulfate ions. Okay. And then a similar thing can be said for the chromiums. I need this chromium this chromium gaining 3 electrons has to occur twice. Now I've already got 2 chromiums here, but I need 2 chromiums here to complete that. Okay. Those 2 chromiums have to combine, or have to, each of those chromiums undergoes this reaction. So I need 2 of these Cr3 pluses on this side. Alright, so that does the balancing, the change in oxidation number. Now we check to see if the major atoms are balanced. I believe they are. 2 chromiums on the left, 2 chromiums on the right, 3 sulfurs on the left, 3 sulfurs on the right. There you go, so chromiums are balanced. Now we balance the oxygens by adding water. On the left side, left-hand side oxygens, we have 7 plus 9, so a total of 16. Right-hand side oxygen, we have 12. So I need to add 4 waters to this side. Okay. Next, we balance the hydrogens. Left-hand side hydrogens, we have nothing. Right-hand side hydrogens, we have 8. So we add 8H plus to this side. Okay, there you go. And then that should balance everything out. Now, one final thing that I forgot to mention in my steps was final check charges. Final check charges. Okay. So on the left-hand side, we have a total charge of, let's see, 8 plus. So charge, we have plus 8, but then we also have a minus 2 and then a minus 6 here. Yeah, minus 6. So plus negative 2 plus negative 6. On the right-hand side, we have a charge of plus 6 from the 2 chromium 3 pluses. And then we have a charge of minus 6 from the sulfate ions. So overall charge is 0 on the left, overall charge is 0 on the right. So my charges balance out. So we're done. So the overall reaction, the overall balanced reaction will look like this. 8H plus Cr2O7 2 minus plus 3SO3 2 minus going to 2Cr3 plus 3SO4 2 minus plus 4H2O. There we go. And there is the balanced reaction. Another balanced reaction using oxidation numbers. Alright, so as you can see, this method, after these last two examples, this method is a little faster, especially if you can identify what the oxidation number, or what oxidation numbers are changing, which will tell you what the reduction and oxidation reactions are. Okay, I'll go through one more example, but if you feel like you are good to go, then feel free to get started on the assignment. Otherwise, keep watching. Alright, so as in this third example, here we go. So balance AS2O3 plus NO3 minus going to H3ASO4 plus N2O3. Alright, make sure I got all my charges correct. Yep, okay. Alright, so doing oxidation numbers again. Here, oxygen's minus 2. The AS would then be, I believe, plus 3. Okay, over here, the oxidation number of oxygen is still minus 2. But we've got hydrogens now. So the oxidation number of this will be plus 1. Which means the AS, the astatine, has an oxidation number of, let's see, this is minus 8 plus 3, so this will be plus 5. Right, over here, oxygen, oxidation number minus 2, which means the nitrogen has an oxidation number of, let's see, 3 times negative 2 is negative 6, but has to go to minus 1, so nitrogen is plus 5. Do the same thing over here. Minus, oops, not minus 5, minus 2, altogether minus 6, but the nitrogen, oh, I've got 2 nitrogens, so it's going to be, I believe, a plus 3. Alright, change, time to see the change. The change here, change in oxidation number is plus, no, it's not plus, it's minus, it's a minus 2, okay. And then the change in the astatine, oxidation number change here is going from a plus 3 to a plus 5, so this will be a plus 2. Alright, now, turns out that in this case, everything, the oxidation number change balances out quite nicely. So we don't actually have to do anything. Yeah. Oxidation number change is already balanced, so we are good to go on that side. Alright. Next step, balance non-major, or sorry, non oxygen non-hydrogen atoms or balanced major atoms. So let's see, I've got one astatine here. I've got two astatine here, one here, so I need to put a 2 here. Just same with nitrogen, I've got one nitrogen on the left, two nitrogen on the right, so I'll put a 2 there. Okay, that works out nicely. And then after we balance the major ones, we balance the oxygens by adding water. Let's write this down. Left-hand side oxygen, right-hand side oxygen. So left-hand side we have 3 plus 6, so we have 9. On the right-hand side we have 2 times 4 is 8, plus 3 is 11, so I need to add 2 waters on this side. Then we add hydrogens. Left-hand side hydrogens, we've got 4. Right-hand side hydrogens, we've got 6. So we've actually got to add the hydrogens to the same side we add water. Interesting. Oops, that's weird. I don't know why that step is showing up there. But let's add 2 hydrogens here, and that should do it. Okay, let me just erase these things so that they don't get in the way. That's just weird. Alright, so if everything should check, we'll check charges. Make sure everything is good. We have 2 positives, 2 negatives, so overall charge is 0 on the left. On the right, we have charge of 0 because nothing is charged on the right. So there you go, charges are all good, and everything works out quite nicely. There you go. So that's the method for balancing redox reactions using oxidation numbers. These last couple, the 3 examples we did, showcased it's the strength of using oxidation numbers because they went by a lot faster than when using half reactions. But again, it does require you to be able to figure out what are the oxidation number changes. I'll give you another example, but I won't actually go through this particular example, not fully at least, but I will show you an example where it might be a little difficult to tell what is the oxidation reaction and what is the reduction reaction. So here we go. So it's KMnO4 plus HCl going to the following. MnCl2 plus Cl2 plus KCl, and then finally some water. There you go. So this reaction is kind of somewhat difficult to tell what is actually going on. Partly because you've got a chlorine, one chlorine on the left, but then on the right side you've got 3 of them. So you don't know which one to pick, right? Is it going to this one, or this one, right? And then once you do decide which one it is, how do you go about balancing the other 2, right? So this type of example, you can do it with oxidation numbers. I'm not really sure which method is easier or which method is faster for a reaction such as this one. Okay. I won't go over something like this, but if you have any questions on your assignment about that you don't quite understand, let me know and I'll go over it with you in class. Alright, good luck with your assignment then, and I will see you guys later.